asset management. And I kind of recently got pulled into working on generation with Andrew here on wind turbines. So we're going to get some nice RUL analysis going here with them and vibration data, and let's kick it off.
Thanks. I should probably let you folks know I work with AES. It's a wind energy company. We own utilities business as well. We do a lot of work with SAS. So just kind of get you guys an idea what we're doing here is we're
their data. Originally, we were working with just sensors off of the turbine, not really looking at vibration. So vibration was another technique for us to go, or another topic for us to tackle within this. And the amount of information that we were bringing through, we had about 110 different turbines in 2 different sites. We had about a month and a half of data, and the vibration information came in at various points. So we had a lot of flexibility within a lot of volatility, I guess, within the data in there. At one point, we brought in about 6 billion rows of data, not rows, well, rows of data across the turbines and cleansed it up to about 1 million or so rows of information across to do signal processing, in which allows us to look at the features of the data to do the RUL, the remaining useful life analysis. And that went through a classification process where we actually looked at the information that's coming through and validated the data before we did the modeling. And this reduced a lot of the overhead that we had to do with remaining useful life, which is basically a regression analysis that we did. We'll talk a little bit more of that as we move through this. We made it so that it was operational. So we made it so that we can bring in any turbine, any site, and bring the data in. So SAS consumes the data. We look at the file that's coming in, evaluate the variables that we have. We basically have time series data, site location, turbine information, and the time series elements within the measures. And with that, we can basically automate the process to work this conceivably across any turbine or any data relative to the naming conventions and whatnot, and do it a unsupervised type of process to this. This really makes it feasible for them to go from one site and bring another 3 or 4 sites in and just actually move the data through the process without having to do a lot of recoding and redevelopment on that. And that works for continuous improvement, so being able to track this. One of the most important portions of the phase, we'll talk a little bit more detail on this, is in the data quality section of that. But let's talk a little bit more about the turbines themselves.
all right. So kind of peel back the curtain a little bit for folks that don't know what's in a wind turbine or what's up there. On the top left here, you can see this. This is how our turbines are set up tower. We got the blades and the rotor, and then that spins with the wind, which spins a bearing, which is known as the main bearing. Then that spins a shaft, that goes into the gearbox. So this blue part here is the gearbox. You have the planetary, which is low speed side, intermediate, and high speed throughout there, and that steps up the RPMs of the rotational speed of the rotor to get it to be fast enough for the generator to be able to produce electricity. And those are the main components. That whole setup there, the main bearing, gearbox, and generator is what we call the drivetrain of a wind turbine. And that's the major parts that we want to consider and look at and have everything set up in a way that makes sense. And so this allows us to do some monitoring, and also we can use vibration data to understand the health of each of our components and be able to figure out what's going on with our main bearing over here, what's going on with our gearbox, and what's also going on with the generator. And this really allows us to get a good idea of health indications as well. So the way that's set up here is you have our vibration data. On the main bearing, we're just looking at the bearing itself. It's just one big, humongous bearing. When we go to the gearbox, we're looking at the gears and bearings. There'll be various stages that we're looking at with the vibration data. And then after that, there's going to be the generator, where we'll look at the drive-in and non-drive-in bearings of that generator. And one really interesting, I guess, curveball that threw Tom, I didn't really tell him this until we showed him the data, is that this vibration data has got 5 power classes. So not only do you have continuous data going through, when there is a time for the data to actually be collected, so what happens to the vibration system is that it'll wait for the turbine to be running, and if it's at a good running state, then it'll start collecting data. So you have lots of gaps in the data, and I'm like, yeah, we got 6 million rows of data, Tom, and next thing you know is you can only use about 200,000 of it. So it's kind of, and it's all sporadic and spaced out, and so we had to put it all together and do all kinds of fun things with our data quality, we'll get to in a minute here. But after that, we had also had to go through each power class. So now we have these 3,000 rows or 300,000 rows of data we can mess with, and we find out we have enough coverage for 2 of the 5 power classes. Now we can only use the operational limits for power class 4 or power class 5, and we got them for all 5 power classes. So it's kind of fun to figure out how to get that data in a way we can actually utilize it, because we have alarm limits for each of the power classes, because the power classes are designed by different levels of the turbines generating at and getting to, so we can actually evaluate the vibration of the turbine, of those components in that turbine. So that will allow us to have the right thresholds, because when it's in the power class 1, it's just starting up, so there's a lot of volatility, just like when you have a gas plant just starting up, you have a lot of different volatility as well. Then it kind of settles in, and then after that it starts ramping up to rated power. And then once you get from ramp up to rated power, there's a little bit of resonance frequencies that can happen as well, so that's going to change your thresholds. And then you move on to the rated power, which is power class 5, and that's when we're running and producing full electricity and full power of the turbine.
And you'll see some of that in our reporting as well on that. And the power classes, how I kind of thought of that is it's kind of like gears in a car, 5-speed, 4-speed, 3-speed, and you're slowly shifting through it. And the unique thing about when we had to do the data engineering with the power classes, is that there's 5 different models. There's 3 or 4 different models, depending on how many power classes the turbine would have. You can't combine the power classes. You have to keep them separate, and then combine them at the end and do through rationalization of the data to be able to do that. So we went through a data engineering phase with this, and bringing in that information, parsing it out, cleaning it out, to getting it to where we could actually consume the data, and to be able to make it so you could actually do analysis on it. Just the raw data coming in, there was such, as he was saying, there's a bunch of holes and blanks in the data in here. You can fill it in, but it's not really going to work that way for us in here. So all of the information that he was bringing in, we actually have now the forensics that he can go back to his other engineers and say, hey, look, guys, I don't have enough data on this, and this is why. You could see the gaps in the data, and we do that proven for him in this process.
All right, now we're getting to the good stuff here. So how the heck are we doing this? So the first setup here, we've got our data quality setup, where we are looking at various things we're talking about. Look at our observations and count thresholds to make sure we have the right amount of data for that power class. So if we're looking at power class 1, do we have enough data coverage to do a good analysis? Same with power class 2 and 5 and so on. And then we look and see if there's any missing data, any null values, and get a null percentage to see how we can evaluate whether we should use that time frame or not. Then we go through and get our time gaps, and we finally get an idea of how much sampling we have. Is it irregular? Is it regular enough? Is it okay for us to actually utilize? And then we go and make sure we get rid of a lot of our duplicate timestamps. So what could happen on this data is we have a turbine ramping up to rated power, and as it's on its way to rated power, you have a bunch of different snippets of data that are sporadically being collected, essentially, and you might have timestamps overlapping, because what could happen is you might be in power class 1, but it's going up to, like, say, power class 4. So now we have some data for power class 1, 2, 3, and 4, but we're hanging out in power class 4 the longest. That's going to be the best, richest data set. Power classes 1 and 2 are not as great, so we might throw those out because we're ramping up to a certain level based off the wind speed. And we have the wind speed with it, so we can detect where we should have been at and what power class is a better one to be utilizing as well for that situation too, to help us rule out any of the data or production data we might want to use. And up here, we got an example where you can see that we're looking at this particular turbine here, or this value here, where we can check and see that data is available, and we want to get an idea of how our quality is. So here we have a measure of that data quality and coverage, and we have enough about availability here. And then down here, if you click on one of these in the SAS visual analytics platforms, you'll see the data of each power class, how it flows through. And so you can really see that it's here, and then it comes down, and you get a lot of good, rich data set here. And so we want to utilize those portions of the data to have a good quality data set to do a good analysis. And so we want to set this up to be able to rule out anything that's going to throw out any false positives and false negatives, because a lot of times we'll have situations that we talked about earlier, like, hey, this bearing looks really bad, it's going to fail in 6 months. We go order the parts, and we go up to look at it, and we find out that, no, it's actually fine, we just need to grease the bearing. So now we are wasting some time and things like that. So we want to eliminate those types of false positives.
Yeah, a few things on that. When we first started this project, when we were running through the process, it was literally running for 30 minutes or so, going through all the data, cranking through it. Without doing this type of step through this, it would take us probably an hour and a half to run the process through. Even now with all the data, it's so rich that we're running the process. It still takes us to go through the 110 different turbines in one sweep, along with the 5 different power classes, doing 5 different models per each turbine. It still takes us about 20 minutes to run through those at that time, which is actually pretty good in that process. But the big thing about this is we're not wasting time. We're able to see really quickly that, hey, which turbines can I run on, or where am I not receiving data? So this data quality check actually is an operational check as well for us to determine whether or not the turbine's actually receiving or sending information.
Yeah, that's a good point, because a lot of times we'll have analysis we'll want to do, and we find out we have the data, so then I have to go figure out how to get it. A couple of situations could happen where I might go to our OEM and go, hey, what's going on with the system? This turbine's not getting good data coverage, the other ones are, and then we can actually help get them to see that they're actually having an issue with that control box, or there might be a no-com issue or a data connection type issue. Then we go up and fix it proactively, which is also a nice thing to have. All right, so now getting into our health indicators, this is probably the meat of what we're doing here besides data quality. Here we're using a couple of approaches. One of them is the Z-score. The reason we're using the Z-score is because we want to standardize our data set or normalize our data set, because what's going on here is since we have sporadic data points and data ranges of data, we want to make sure they're normalized so we can actually do a good evaluation on those. Along with that, we're also normalizing our alert values, our alarm values. So you can see up here you have measure Z, which is going to be the Z value for our measures coming in. We're normalizing our warning thresholds and our alarm thresholds. The reason we're doing that is because we're looking at a brand new wind farm that hasn't had any failures yet. And so in order to be able to run the main useful life without having the failures, we need to be able to utilize the warning thresholds that we already have set up, because we know what bad looks like, we know what good looks like, but we need to be able to put that into the model. So being able to normalize it based off the sporadic data, we can actually keep everything together and have an apples to apples comparison where we have our normalized data and our normalized alarms. And then from there, we take it into a health indicator. So we look at the analysis here, and we're able to use right here, we're able to transform our Z-scores into a health index from 0 to 100 based off the behavior of the vibration data. One of our dashboards you can see here, this is one of my favorite screens that we've developed, is we're able to, as an analyst or as an engineer looking into what do I need to look at today or what do I need to tell the site there's an issue from, I can quickly come here and look for what's in a warning. I can click on it and it'll show me all the different power classes that are associated with that situation and what's in warning, what's in alert. I can click on that and get all the information about each sensor. And so in this case, we had an issue with the drive-in generator bearing 2 times running speed. This particular tag is a great one to look at when you want to find out if there's misalignment in your generator. So that could be the generator and the gearbox misaligned. So in that photo, when we saw the gearbox with the gearbox is a floating gearbox, which means it can move around on bushings, but it stays solid. So that can move around a lot based off the wind turbine, and the generator is bolted down. So if that generator is moving too much or oscillating too much, we could see that misalignment in this sensor value here. And you can see when we click on that sensor value here, you have this orange setup here. This is our alarm level for that particular power class, and we can see when our data comes up. And keep in mind here, we're looking at the slope of the sensor values. That's what we're doing with the Z-scores. And we're able to see when we're getting above a threshold and not above a threshold. And looking at the, actually the training's on the next slide, sorry. But looking at these health scores, you can see where we need to look at it and how long we're there. And if we start seeing the data is actually hanging out consistently up there, that's when we want to start taking actions. If it's going in and out, that could be that it's a sign of an early indication of something, but not quite an action need to be taken yet. Is there anything I missed?
Well, a little bit of clarity on this. We're not actually looking at the slope right yet. Basically, this is the portion right into now. We're doing the analysis right now to identify the issues that we're having in the turbine. This next slide is going to show us now we're going to the point where we're doing RUL. And basically, the slope value is equivalent to saying how many days till the event's going to happen within this. So this is now when we get to the next sweet spot level linears, which got kind of that stages that we were talking about in the process. Now we're going into the RUL.
Thanks for helping me out there, Tom. All right, so this is where we're talking about the slopes here. This is the really fun part where we're getting to a place that a lot of folks have not gotten to in our industry, being the wind energy industry. And so here we're taking that the same setup here where we're looking at our robust regression, and this is the code we're using there within SAS code. as one of our setups. So we're trying to get our slopes with the robust reg that builds the slopes, and then we use that to put in these other models. One really neat one I think we are using here is the Kendall-Tao method. Kendall-Tao, that one's really neat because you can see something. It's kind of like a situation where you look at something from afar and it looks okay, but you want to make sure, so you get closer up and you find out, no, it's actually not okay. We might need to do something. So it's kind of neat to be able to use that type of an analysis to really get a good indication of what's going on, especially when we have this sporadic data. It's really helpful to see, hey, that looks like from afar it's good, but then you get close up and it's not as great as you thought. And so what was really neat here on this dashboard slide we have, you can select the turbine in the morning. It'll give you the same sensor listing out and show you which ones are stable and trending. This is coming from our Kendall-Tao, letting us know if the data is sorry, this one's coming from Kendall-Tao, excuse me, the trend confidence. This guy here is coming from our robust regression here. It's showing us stable or trending data. If it's trending, you'll see that it's either trending up or down, and it's making a change. It's not actually stable and straight. And then the high or the low confidence is what the Kendall-Tao is using to tell us if it's something we should take a look at or not. Bringing it up close to say, yeah, actually it is bad, or no, it's fine, just leave it alone. And you can see in this trends here, we're showing the slopes. And so you can see the blues, the alarm levels. The orange back there is kind of hard to see, but that's the moving average of our data. And then the green is the slope change of the data of that sensor value, which is the same gen non-drive and 2 times running speed. And you can see in the power class 1, it kind of has some stuff going on, and then 2 and 3 it settles down, but in power class 4 it starts to get really more above that threshold consistently. So this is something we'd want to take a look at. This could be a sign of a misalignment issue, or it could be a sign of a bad bearing starting to come. But when we get into the frequency analysis on this particular one, you can see that as just a signs of misalignment, which is a very classic situation in this type of wind turbine. Is you always really early on we see misalignment on the drive end or non-drive end generator bearings pretty consistently in this turbine model, which is the SAS Viya 150. And then we got a little bit more deeper into our setup here. I wanted to show you guys some of the code we used. This is the robust reg we used, and this is how we got the slopes, and then we put that into our slope estimate code here, and this is allowing us to get the same screen we were talking about earlier, where you can look and see how the slopes are trending. This also allowed us to get a classification of things, whether they're trending, stable, or indeterminate. So if we had a setup that showed that the turbine was in an alarm state or a warning state, and if we saw that it was insufficient, then we know that we wouldn't be able to use that because it's got insufficient data, so we wouldn't want to take an action on that. But if we see that it's stable, then that's a good opportunity to look at. And also if it's trending, and we know we definitely want to take a look at it because it's going upward or downward. And one really neat thing about this is that we're able to assess remaining useful life on an asset in a positive manner and a negative manner. So say for example, we see a turbine's running and it has an alarm state, and we need to take an action. Say it might be, hey, let's go grease that bearing. We went and greased that bearing, and then we can see that the RUL changes in a positive manner. So it starts trending back downward away from that alarm. So now you have an adder and a detractor from your asset health score. And I think that's a big deal because we want to be able to get very accurate with these health scores and these remaining useful life levels as well.
No, you did great. Yeah, a little more detail though on the variables that we're using in here. As you can see in the code in the center there for the robust reg, we have a high equals time days. What we did with the times days is basically your time series data, and where time series is down to milliseconds in this case. But we basically convert that to a numeric value. And when we're going through the data cleansing process, we're looking for the first event happening or the first read being done, and we start counting those times days at that point. So we make that numeric value so that each times day is actually, for each model, is sort of unique on that. So we normalize, we get rid of the time series element of it, and basically just to have a numerical value to trace through it. Because in our slope, we really don't care about time about this. We're just looking at the sequence of data coming across that. And it also allows us to find gaps in data if we have missing portions within those. The high value is the health indicator value. And when we were mentioning about the measure Z value that we're receiving, so when you normalize your data using the Z values within that, you're looking at normalization around above and below 0 values on here. And if you go above, generally if you go to like a 1, you're kind of like, okay, you're getting a little bit out of a norm. If you go to a 2, you're getting a little more out of the norm. And when you hit a 3, generally that's an anomaly that's happening. And that's when you have any kind of series or high frequency data that we're working with on that. You can use that z-value score to normalize your data and use that as an indicator of how well that particular variable is performing, or those values are performing. And that's how we're doing it, the non-discrete way of being able to look at a numeric value, and I don't care whether I'm working in 10,000s or 10,000s or 100 space, whatever. It basically normalizes that data around that zero value, if you will, on that. So that's how we come up with our slope when we go through that. And then we just carry that over. The output from our robust reg goes into the Kendall-Tau correlation on that. And basically what that's doing is you're going to look at how many, it's going to score that reg, or that slope, about how many outliers we have on here. And the better value we get within that Kendall reg output on that tells us whether or not we have a good slope or we have a messy slope, right? We want a tight slope to know that we're having a good trend. And that's when we say we have a trending on here. So that's why we can have trending in a good stable area, and also we can have trending when it's bad. And that's where we come up with the confidence levels for the high and the low values within those.
Yeah, it's allowing us to get rid of the noise and stick to just looking at the signal, which is really nice, really neat. All right, and then the next thing we just started looking at is our distance to our alarm level. So we have the slopes, and we're looking at our warning levels, and we have this data coming in, and we want to be able to look at how far are we off from our alert levels. And so we're able to track that here with the sensor data. In our dashboard, you can click on any one of these turbines, and it'll show you how you're doing. And so we can see our measures, how they're tracking, and we can see the alarm level, and we can see when these are above the alarm level. You can see up here, everything's looking good, but when it's above the alarm, it's actually negative. So it's really showing us where there's negative or detractors from our health score. So we can make sure so we can actually start looking at different indications of where we should look at for RUL. This allows us to get a good idea of what we're looking at with our data, and also with this, we were able to put in some safeguards. One of the main ones here is we're able to compute RUL only when these set standards are met within our data, because we have so much we have so much sparsity in our data. So if our slope is greater than 0, if we have trend confidence meeting our criteria, and we have our data quality gates are all passed, then we can run this analysis and have a good indication of what's going on with the turbine with respect to remaining useful life. This avoids us from having any of those false positives we were talking about earlier, where we say the turbine's going to fail, and then or the bearing's going to fail in 6 months. We go grease it, and it's fine for 5 years. We want to eliminate those types of situations, and it's not fun when you tell an operator that their bearing's going to fail, and then they go bring everything in, and you get up there, and all they had to do was grease it, and then, or actually, a funny one I had, we thought all the bearings were going to fail in the whole site, and we found out when we got up there, thankfully before buying bearings, that we had these automatic lubrication cups that were on the bearings, and this is in Palm Springs, so it's in the desert in California where it gets really hot. They were supposed to use air in a spring to push grease in when there's a difference in air pressure. Well, the problem was the grease got so hot that it caked inside those canisters, and the grease never came out. So we had this, oh my God, the bearings are failing. We're going to lose all the bearings at the site of a 50 wind turbine site, all because we had these grease cups not working. So we went back to manual greasing, and everything worked out fine after that with that site. And so now we go back to sticking to that type of a process. But this would have helped us find that as well, and eliminate those false positive alarms as well. Is there anything you want to add?
Yeah, so I think one of the real key things here is at the end there we're making it, is it physically plausible, statistically defensible, and is it operational and actionable, and how do you get to that state within this? Through the phases that we went through to be able to get to this, the solution on this, you had to have the data, you had to have the data cleansed. To make it plausible, if there's a question that happens within this turbine, within this look, you can go right back to the data report and say, hey, this turbine had enough data in this. It's feasible to do this. We actually have a feasibility score on that. It'll either throw it out or bring it in to that. If we're not getting reports enough for a particular site, we can say that, hey, we don't have enough plausible data in this area, so it's defensible in that portion of it. And then working statistically through that data in here, the two main procedures that we're doing, the correlation and the regression in here, are very simple. You saw the code that we ran for that. They're literally like 3 or 4 lines of code that we put in for, and that's just the power of working with SAS. It's a really robust regression that's going in there, but it actually really does prove out, because the data has been stable and brought forth. You can really defend that because it provides you with actually the back-end reports of that to determine whether or not, you have a viable output from that standpoint on here. It all goes back into that data quality, though. Do I have that information that's coming in? And when someone goes to Andrew and says, "Hey, is that actually really working in here?" You can defend it based on those two procedures in there, but also you can go back to the data and say, "Yes, I have data on this, and this is plausible." When they say that why aren't you reporting on T10? He can say, "Well, you don't give me enough data," which is one of the things. They're like, "You don't give me enough information." That's like when he gave the data to me, and I only got 30 records on this. I'm like, "You gave me 6 million rows. That's great, but they're all missing. So go back and figure that out, right, and get that working." And then we'll talk a little bit more about plausibility, I think, as we conclude the process here.
Yeah, no, it was nice too because when we found an issue, I can go to the OEM, say, "Hey, this bearing needs to be looked at. You guys need to do your due diligence to make sure that this bearing is not going to fail prematurely." And they would, at first, they go, "No, no, no, you're talking about." And then when we start showing them this type of analysis, they're like, "Whoa, okay, we'll definitely do a technical service like request for you and get it looked at." And it was amazing how quickly they reacted when they saw this stuff. Because normally they're used to a customer going, it's bad, hey, 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 hey," and not have any data to back it up. So it was really neat to be able to show them this. And what was really fun is we had more stuff than they had on their own turbine, and they're the one running it. We're just watching them monitor because with our warranty for a new wind farm, the service and maintenance contract you have with the OEM is there for usually 2 to 5 years, and we're doing a lot of shadow monitoring. So it was really fun to find things that their team didn't find. And now some of them love me, some of them hate me because I find what they don't find. So it's kind of fun to have that kind of situation there. But with that, we'll roll on to our next slide.
Yeah, so when Andrew and I first started working together, what was it, 20 years ago? Feels like it, right? Yeah. Literally about 5 years ago, I guess, right, initially. Yeah, yeah. When we first started working with it, he had never coded before. He's an engineer, smart guy, knows his stuff, knows everything around that, but he's never coded before. So when we turned it in, we went through visual analytics with SAS first to bring him through to, hey, understand your data, where you're going with on that. And then we moved just organically really into a SAS Studio type realm and getting into more programming in that, and then combining that in with the visualization tools in here. So that now when we develop these process flows like you see here, and we have decisioning in there in the center there, we actually have decisioning in the fact as far as what data are we going to use and what data are we going to run with on this, to operationalize this. He can go to this and actually take this process and run these, what we call these swim lanes in SAS Studio, if we go back into the programming world here, and run these in, he only has to run the top once, and then he can run the other ones in succession, and select the turbines that he needs to run with or not run with, or whatever on here. Each process in here is actually part of the phase. The data engineering actually is the first portion of that. The first phase in there, and then we go to the second and the third phases where we're taking in threshold data, and then we're doing health scoring, modeling in the center across that. We're looking at for outliers on the fourth one in there, and on the bottom one on the crosser, that's where you're doing the RUL process in here. So it's actually the life structure of the project that we were working from in here. It's documented and traceable from this process. And now he can hand this off to his other new engineers to actually run this and operate this process for them if he needed to on here. Our next big goal on here, and we're excited to kind of work on this stuff on the side as well, is we're going to continue a little bit more on this and go even further into this with automated decisioning, and probably bring in some more AI type of element into this process as well in there. But with that, I think we'd like to take in some questions. I'd love to know if anyone out here has been doing any kind of signal processing analysis similar to this, and what techniques you might be using, or if you have any questions for us as far as how this might be useful in your world.
any signal analysis, as you know, Tom. That's not my thing. Yeah, but how was this received by management and the folks ultimately responsible for the turbines?
Originally it was really, they were just a typical response was like, oh yeah, whatever, we know better than you, was the initial response, because that's how it usually is in our industry, unfortunately, with the OEM. But once we started giving them a good report and a good backup, this really started 4 years ago, getting this rapport with this OEM. Because 4 years ago, we did a different model with SAS, with the SAS platform. We actually created a moving windows principal components analysis that runs every day on our data, all of our sensor data. And I found some leaks in our cooling system at our Hawaii wind farm, being in Palm Springs. And it was fun being able to tell the technicians, and that site was a fun site because we had a good rapport with the site manager there. At corporate, it was a little different. But when we got to that spot there, where we asked them, hey, can you guys check this turbine out? It looks like there's a leak in the cooling system. I went and found like actual live data too, and showed them how it was trending down over like a month period, how it started trending a lot more negatively. And I showed them on the MWPCA model how it flagged it for a couple days. And I was like, well, if it's coming for a couple days, it probably really is a problem. Because sometimes it'd be a false positive, and then we'd not worry about it. But if it kept going, so when we showed them that, they went and tried to fix the leak. And then the next day I checked the turbine and it still was leaking. And I told our site manager on our side, and I said, hey, turbine 5 is still leaking. And he's like, no, they fixed it yesterday. I go, no, look, MWPCA went off again. Here's the data trends again. And so he sent them back out there, and they searched that whole nacelle, and they found a leak. It was a really small leak in the hose in the very, very back of the nacelle where no one ever walks around and goes to, and that's where the leak was at. And they're like, how the hell did this kid in California find this crap? And we're looking at this whole thing all the time and didn't even find this thing. So from that situation 4 or 5 years ago to now, I've developed a rapport with this OEM that we're not messing around. We're really looking at real things. Yeah, I might say if something's bad before you think it's bad, but I have this backup to tell you that it's going to be bad sooner than you think. And so it's been fun having those kinds of conversations with them now. So they're more receptive, especially when I give them a nice report out from here with their, and what I do now a lot of times, our operations site leader at the site for the OEM, because we have our guy and their guy in our office. And so for the OEM guy, what I'll do is I'll fill out all the information he needs in his report to send out what they call a TSL ticket, which is like a technical ticket or whatever. And so I ask him, what do you need in your ticket? And I start the report off with everything he needs to fill out. And then I have my analysis afterwards with these outputs and things like that. And they respond so quickly now. But that's really because we put a lot of the work and effort into it. So now it's quick, but before it wasn't. Hope that answers your question.
Like the service with the OEM, or will you use this as your primary?
So our model is to be use a service agreement with the OEM for the warranty period. Once that's over, we flip over to self-perform. We're big on self-performance. So half of our fleet right now is self-perform fleet, and half of it's new turbines that are being under a service maintenance agreement. Oh, for sure. And what's fun now too is having these models now. I can tell because I've recently switched over from our operations side to our construction side, and so I'm actually getting involved in our contracts that we have with these OEMs. And this type of data that we need on the O&M side, I put in our contracts now. And so we're getting our data when we want it. So like if there's a brand new site they want to build, before we give them the final stamp of approval, I get my vibration data before. And it's fun now because even our VP of engineering will come up and say, hey, did Andrew get his vibration data? And I'll be like, no. He'll be like, okay, well, don't sign that substantial completion document yet until he gets his data, because he needs that. So it's really fun to have that type of rapport within the organization, and also to have that push on the OEM to get it to us now. Are there any other questions? All right. Well, we're not going to get in your way between the next thing and us. Or are you in the next thing? Thank you guys for coming out. Really appreciate it.